So I'm going to begin today's story with a lecture. No, sorry, wrong way. I'm going to begin today's lecture with a story. On Friday, I was picking up Cam and Kayla at their elementary school, and I talked to their kindergarten and second grade teachers. And the question was, how do you explain to kids -2 times -3? And so I know some of you started to hear this as you came into class early. I immediately said that this is the wrong question to start with. You don't start off by talking about -2 times -3, because you have two things going on here. You have the magnitudes and you have the sign. You first want to understand what's going on with the sign, with -1 times -1. Then think of the 2's and the 3's as dilations. And so I said, really, one way you could do it is you could say, well, I start off with $1. I give you $1, and then you give me the dollar back. There's a -1, I'm giving the money to you, and -1, you're giving it back to me. The negative times the negative is a positive. Then we talked a little bit about walking on the real number line. When things are positive, you're walking forward. When things are negative, you're walking back. And what happens is you have a magnitude, 1 step, 2 step, 3 steps. And when you multiply by -1, that just flips you like this. Now actually the camera might not be able to see that if I swivel, so I won't do that. Well, as soon as you start to say this, I'm walking and the negative sign flips me 180 degrees, this should be a very natural question. What's the natural question?
How do you turn back?
Well, one is how you turn back, or you can just do it again. And we have this beautiful operation of 180 degrees. What else should we be asking or thinking about?
Why 180?
Why 180 degrees? Why not an arbitrary degree? And this is where we start getting complex analysis, and z equals r e to the I theta. Now, for the record, I have not committed yet to doing this to Kayla's kindergarten or Cam's second grade class yet. I want to see how it goes with the college students first, and then if it goes really well, maybe try to talk about complex analysis in the elementary school. Probably not, though. But if you think about it, if you think about going back to the basics as to how do you decide what -1 times -1 is, what we're really doing is we have a vector. Vectors have magnitudes, and vectors have direction. And when we're doing things in complex analysis, we're just allowing ourselves to have other directions as well. All right, so complex numbers. Not surprisingly, we use z as its... Why do we use z? After x and y. We don't have much originality. Z equals x plus iy. I am, or I is the square root of -1. X and y are real. Z bar is the complex conjugate, is x minus iy. Z times z bar is the length of z squared, is x squared plus y squared. We will sometimes write z as r e to the I theta. E to the u is the sum, n goes from 0 to infinity, of u to the n over n factorial. E to the u, e to the v is e to the u plus v. And this is the binomial theorem. So I believe we've talked about this in this semester at some point. I know I've talked about it in at least 2, if not all 3 of my classes so far, so I think it's pretty safe. If not, just watch one of my videos from somewhere. The exponential function converges for all values of u. This is an extremely nice function. So you give me any value of u, this is well defined. If I give you a function f of z equals the sum, n goes from n0 to infinity of an z minus z0 to the n, we'll say that this is a Taylor series expansion or a series expansion of the function about the point z0. We might not want to say Taylor series if n is allowed to, if n0 is negative, because then you've got a couple of reciprocals in the beginning, and this function would blow up at the point z0. So for instance, if n0 is -5, you start off with a 1 over z minus z0 to the 5th term. And so if n0 is less than 0, we say it's a pole of order negative n0. If n0 is greater than 0, we say it has a 0 of order n0. A function is entire if it's differentiable everywhere. And of course, when we talk about differentiable, we mean differentiable as a complex function. So I'm not going to go into too much of the nuts and bolts. We only have one day. We write holomorphic for differentiable. It makes it seem like we're doing something better. All right. It's really the same thing. So what does it mean for a function of a real variable to be differentiable? Real variable, calc 1, what does it mean for a function of a real variable to be differentiable? Okay, so g is from R to R, g prime of x is what? Okay, so the standard definition. So for a complex function, what do we change? No. H is fine. We can keep h as is. What do we change? X to z. It's a very difficult subject, okay? I mean, this is not easy. F prime of z is the limit as h goes to 0 of f of z plus h minus f of z over h. Normally when I teach Calc 3, I actually have borderline violating child labor laws. I have the little kids in preschool classes drawing the secret of Calc 3. It also works for complex analysis. How many of you have seen Karate Kid 2 when he goes to Japan? You learn the secret of Miyagi karate? No? So culturally literate. All right. Think back to one variable. Can someone tell me the kinds of paths I can use? Okay. Wow, you've enumerated every single path in less than 2 seconds. These are your possibilities. That's basically it in one dimension. Something like that is a valid path. The limit must exist independent of the path. Because of that, it is a far stronger statement to be complex differentiable than to be real differentiable. And this is one of the reasons why complex analysis is such a strange subject. You could not compare complex analysis to standard real analysis. You cannot compare it to standard real variable functions. What you want to do is you want to compare it to functions from like the Green's theorem, Stokes' theorem. Functions that are very, very nice. And what's really going on here when you're trying to compare the difference between real and complex is you have so many different paths. Does anybody remember what it means to be differentiable as a function of 2 variables in, say, Calc 3? It's very dangerous asking this question, but at least nobody in the audience took Calc 3 with me. What does it mean?
Isn't the limit must exist in each component independently of the others?
That's not enough. It is possible to have partial f, partial x exist, and partial f, partial y exist, and the function not to be.
Oh, it has to be equal.
No, because no, it's not about them being equal. If the derivatives, if the partial derivatives exist and are continuous, then that's actually enough to force differentiability. But just the existence of the partial derivatives does not force the function to be differentiable. You need to look at like a linear expansion approximation. What's really going on with the definition of the derivative is g of x plus h minus g of x minus g prime of x times h divided by h. Take the limit, h goes to 0. You have this linear approximation to your function. And this linear approximation becomes better and better and better. In fact, it becomes better by a power greater than h. Typically, this would be like h squared, although it just has to be a little bit better than h. What you're doing is you're doing the tangent line approximation, and you're saying the tangent line does a great job. The correct definition of the derivative is to replace the tangent line with the tangent plane or the tangent hyperplane. So there are a huge number of differences between complex analysis and real analysis.
So that's why we use the Jacobian, or that's why the Jacobian is important.
It's one of the reasons, yeah. All right, so do you want to hear the differences between real and complex? Sure. All right, let's see if I can remember them. So I think I often do 4 things when I teach the class. Differences between A and C. So 1, if differentiable, infinitely differentiable, true or false? For R, false. For complex C. Okay. So can you give me an example of a function that is differentiable but not infinitely differentiable? I'll be safe, I'll do x cubed. So something like that is a great example. You know, x cubed sine of 1 over x. The only point that's problematic is the point where x equals 0. Near x equals 0, this is fluctuating, but it's always between -1 and 1. The x cubed will kill it. And so it makes sense to extend this definition to be 0 at 0. Another good function to look at is maybe the antiderivative of the absolute value of x. Okay, it's a real shame that the people who are listening to this at home cannot hear the laughter of the class. This is a really good interactive lecture. I'm really on today. All right. So 1, if differentiable, infinitely differentiable. 2, if infinitely differentiable equal Taylor series in a non-trivial interval about the point. So if my function is infinitely differentiable, okay, not every function that's real differentiable is differentiable infinitely many times. Let's take one of the ones that is, and then at least in that case, I can say that I equal my Taylor series in some non-trivial interval about the point. True or false? False in R. And again, yes over here. Can you give an example? The one we did, yes. F of x is e to the negative 1 over x squared if x does not equal 0, 0 if x equals 0. This function, if you look at its Taylor series, you use L'Hopital's rule, all of its derivatives at the origin is 0. And so the Taylor series would be identically 0. Now the Taylor series does agree with the function at x equals 0. If I was allowed to use profanity, this would be a no blank moment here. But these lectures, I'm really trying to get Disney to put them on its website. My daughter would be thrilled to have me on the same website as Frozen. I have to watch my tongue. I got to be careful what I say. Is it surprising that the Taylor series agrees with the function at 0? No. Because if you look at the definition of the Taylor series, it's f of 0 plus a bunch of things times x, x squared, x cubed, which will all vanish when x equals 0. You're forced to agree at x equals 0. So it's not surprising that we have agreement here. So the interesting thing here is in complex, differentiable equals analytic. So this is a huge theorem, that if you're differentiable, you equal your Taylor series expansion. And in fact, when I say differentiable, you only have to be differentiable once. You're differentiable once, you're differentiable infinitely often, and you equal your power series expansion. And I'll do one more. F is entire implies, I was going to say entire and bounded implies f is constant. So if I have a function which is differentiable everywhere, and it's bounded, it has to be a constant function.
False for R.
Yeah, I thought it would be nice to just flip it up and have at least one yes on this side of the board. So, oh, wait a minute. Oh, no, I didn't flip it up. Oh, well. No. Yes again. Sorry. So can you give me an example of a function that is defined everywhere, differentiable everywhere, real valued, but it's not bounded? I mean, it's bounded, but it's not constant. Sine of x. versus the sine of z is e to the iz minus e to the minus iz all over 2I. And if you look at this, which way should I send z to infinity to have this become unbounded?
Magnitude of z goes to the positive infinity.
That's not enough. If z goes to positive infinity through the reals, this is just the sine of x, and it will be...
Magnitude of z goes to, oh, so take an I.
So take z to either be purely imaginary with a positive or a negative sign. It doesn't matter. One of these terms will explode. So this is a major result. If you have a function which is bounded and differentiable everywhere, if it's complex, it's got to be constant. Okay? It is a very different world. Right? The fact that things like this don't exist make complex analysis a lot easier. All right, so there's going to be a course on this in the spring. Strongly recommend you if you're thinking about graduate school to take it or to see if we will be offering it again the following year. All right, so we've got a bunch of facts about complex functions. What I want to do now is start talking about integration of complex functions. And this is going to be the main reason we care about this. What is the fundamental lie that you are exposed to in Calc 2?
Integration is easy.
Integration is easy, integration is doable, integration can be done in closed form. In general, this is not possible. It is extremely hard to actually integrate something and get a good answer. In 331 right now, the little questions, we're actually doing a unit on integration. And what we're looking at is integrating nice functions over very special intervals. And a lot of times, definite integrals can be done nicely, and you get a really nice answer for a definite integral, even if there is no nice antiderivative. Frequently, the integral of the whole region is nice. But typically, the integration of a small segment is very hard. In complex analysis, the shapes we look at most are integrations over lines, rectangles, circles, nice shapes like that. And if you want, you can think of a line like this as a limit of something like this. And then what I'm going to do is I'm going to let these two tops go off to infinity, let this side go off to infinity, and in the end that should essentially look like integrating over this vertical line. So long as I can show the integration over these pieces is negligible. The idea in complex integration is that if you have a nice function and you integrate it over a closed region, you can convert doing the integration to essentially calculating the residue of the Taylor series or the Laurent series expansion at the places where the function blows up inside the region. And what it's doing outside the region does not matter. So it converts integration to algebra. Is algebra easy? Is it easy to find Taylor series expansions, Laurent series expansions? Yes, at least relative to doing the integration, right? There's a pecking order of difficulty, right? You would much rather do an algebra problem. And by algebra, I don't mean something you would get in commutative algebra. I mean an algebra problem where you're just taking a series expansion and you're playing with things. Let's actually just, I guess, do an algebra problem right now. Let's consider, f of z is 1 over z squared minus 1. Do I want it this way? Plus 1. So what are the troublesome points? I and negative I. So it has poles at plus and minus I. So I have f of z is 1 over z minus I, z plus I. And I want to figure out how to expand this. Let's expand about z equals I. Let's expand about z equals I. All right. Which factor already looks good for z about I? Which one looks good for things about z equals I? Both answers are right if you give me a proper reason for it. So why do you like z plus I?
It doesn't fill the function up.
Yeah, this is well defined. And so in the limit, if I look at, z minus I times f of z, and I take the limit as z goes to I, I'm going to get 1 over 2I. And I can use this method to calculate what the residue is. And I can see, what's the highest power I need to put here so that this is well defined. And that will give me the order of the pole. Unfortunately, if the pole is order greater than 1, it might be hard to get the 1 over z minus I piece. And it's going to turn out later that's the piece we really need. So this is one way to look at what's going on and see how things can be nice. But if I want to expand about z minus I, why might this be the harder piece to look at? I want to expand about the point z equals I. Which piece do you think is more natural?
The one z minus I.
The one that already gives me the z minus I, right? If I didn't even have this piece over here, I'm done with my expansion. It's just 1 over z minus I. So I've got f of z is 1 over z minus I. I'll write it like this, z minus I. And then I've got 1 over z plus I. And I want to rewrite the 1 over z plus I. Well, if z is really close to I want to somehow take that into account, that z is very close to I and expand. What would I love to use to expand over here? I've got a 1 over z plus I. What would I love to use?
Definition of geometric series.
I'd love to use a geometric series. Why might a geometric series be bad? So I want to expand this when z is close to I. Why might a geometric series be horrible here?
1 over z might not be friendly. Or
Well, I've got z plus I. So is 1.1i close to I? Yeah. What's the magnitude of 1.1i? Greater than 1. So if I tried to expand with that in terms of z, I'd be expanding a geometric series with ratio greater than 1. Bad idea. But it's a foolish idea to try to expand this in terms of z, because I'm not trying to do a Taylor series about z. I'm trying to do it about what point? I. So this is where we do one of the two most common things in mathematics. What are the two key ideas we have in proofs for algebraic manipulations? Nope. Add 0, multiply by 1. So do you think we're going to add 0, or do you think we're going to multiply by 1? 50-50 chance. I want to study this. Do I add 0, or do I multiply by 1?
multiply by 1.
So do I want to multiply by 1, or do I want to add 0? I'm sorry?
Multiply by 1.
OK, do I want to add 0, or do I want to multiply by 1? Add 0. Yes, excellent. Why would I want to add 0? I'm trying to expand things in terms of z minus I, in terms of things around I. I've got a z. Do I want z? No. What do I want? I want z minus I. So I want to write this as z minus I to the negative 1, and then 1 over z minus I plus I plus I. And now if I write that, that's going to give me z minus I inverse. And then I have 1 over, this is going to give me a 2i plus z minus I. What's nice about the size of z minus I? So what can you say about the size of z minus I? It's pretty close to 0. So what I'm going to do is, I want to change the denominator by a little bit. What do I want to pull out of the denominator?
2.
Not 2. Be a little bit more. 2i. And so if I pull out 2i, I have 1 over z minus I from this piece. I have a 1 over 2i. And now I have a 1 over 1 plus, in fact, we're going to see we want to pull out a negative. And now if I pull out a negative, well, no, we'll do it this way. All right. 1 minus negative z minus I over 2I. And now this is set up beautifully for the geometric series. But I squared is negative 1. So I can write this as I squared over I, which just becomes I. And so now when I expand, I get 1 over 2I, 1 over z minus I, and then a sum, k goes from 0 to infinity, of I z minus I over 2 to the k. And the series will converge very nicely because this is going to be very small in absolute value. I don't even need the 2. I have the 2. It's nice, but I don't need it. And now you can see the Taylor series expansion very nicely. The pole is going to come when k equals 0. And so when k equals 0, if we just write it out very nicely, what do we get? We get f of z is 1 over 2I, 1 over z minus I. Now we get the k equals 0 term. Oh, sorry, that's the k equals 0 term. Now we get the k equals 1 term. So the z minus I cancels the z minus I. We have an I over 2. That I cancels with this I, so we get, I think, plus 1/4. Then the next one is we multiply by an I over 2. So I think we get I over 8, z minus I, and so on and so on and so on. And so what we see from this is that it's not that bad to calculate the Taylor series expansion. So we started off over here writing our function. We then used the geometric series. And once we had the geometric series at our disposal, we were able to then expand it and see the first few terms without too much trouble. Yes?
How are we able to know that this geometric series expansion is the same as what the Taylor series would be? But this is like a different representation of the function in the series.
Well, I mean, the Taylor series are unique.
And so anytime you have an infinite series.
Well, we've got to be careful because in real variables, I can add the Taylor series of e to the negative 1 over x squared to everything and not have things changed. But since the function is given by its Taylor series expansion, I can start picking off its coefficients one at a time. Imagine they had different constant terms. Then if I take z equals 0 or z equals I, whatever my expansion point is, the constant terms, if they're different, my functions are different. So they've got to have the same constant terms. Subtract the constant terms, and now divide by z and play the game all over again. And you can inductively see that all the coefficients are the same. If there was ever a coefficient that differed, you would then have a different expansion in a small neighborhood. So the Taylor series is unique. This is the Taylor series for the function. You could also get it by taking derivatives of this function. And then the question is that the same as going through all this expansion over here? But I mean, what's nice is this is just simple algebra. We were able to calculate the coefficient of the 1 over z minus I term. And it's going to turn out that that's the only term that really matters when we do all the integration. OK, any questions about this? All right, so it seems like, OK, so we are losing the ability for this to track again. All right. OK, so now it's time to do some examples. So the first example is the following. So let's see. I do have extra batteries, which I hope will work for the next lecture. All right. Let's let our function f of z be z to the n. So it's r to the n, e to the I, theta n. This is the simplest function we can look at. And what we'll do is we want to integrate 1 over 2 pi I, and we'll see in a moment why it's natural to put a 1 over 2 pi I over here. The integral, and the circle here means it's a closed loop. We start and stop at the same point. I'll call this gamma sub r. It'll maybe capital R. It'll be a circle of radius capital R of the function z to the n dz. And so here's the origin. Here is a circle of radius capital R. and we always travel in a counterclockwise manner. Okay, always. And the advantage is when you travel like this, the region is always on your left. Otherwise, it would be on your right. It would just be. So again, does it really matter if the region is on your left or your right? No, but for consistency, you might as well just pick one and stay with it. They've picked counterclockwise, stay counterclockwise. All right, this should remind you, hopefully, of Green-Gauss-Stokes theorem, stuff like that. And so the question is, what is this integration equal to? We could split this up as cosine n theta plus I sine n theta and try to figure it out. Okay? We've got to be a little bit careful because we've got the dz as well. So I'm going to argue a little bit fast and loose. So over here, we really want to parameterize the curve because we're on the boundary. So if I want to parameterize my curve, c of t is cosine t sine t 0 less than equal to t less than equal to 2 pi. Nope. Right now I'm just writing it as a pair of points. You're just walking along the circle, x coordinate, y coordinate. We'll write that as z is, well, instead of using the letter t, I could use the letter theta. Not a big deal. It changed from what you've been doing in real to theta, right? Adding just a small little curve. And we really get z is e to the I theta, 0 less than equal to theta less than equal to 2 pi. But is this right, or did I make a small mistake? Yeah, I forgot a big R. Because normally when you do this problem, you always assume the circle has radius 1. It's not much more work to do the general circle, so why not do the general circle? So we'll assume the circle is z equals r e to the I theta. So what would dz be? It would be r e to the I theta, and then I d theta. I'm not being rigorous here. We only have a day, maybe a day and a half. So we'll just assume that this is the derivative. If you're not comfortable with this, you just go through things the long way and you see what it's looking like. Write this as cosine theta plus I sine theta. See what happens when you take the derivative. You're going to have this I coming in and changing things. And we started the beginning of the class by talking about multiplying two numbers and getting to complex. So it's time to return to kindergarten mathematics. Okay? When you multiply -1 times -1, you get +1. 180 times 180 is 360. -1 times -1 is e to the I pi. E to the I pi is e to the 2 pi I is 1. When you multiply something by I times I is e to the I pi over 2, e to the I pi over 2. That's e to the I pi. That's the famous Euler formula. It's -1. When you multiply something by I, you're essentially rotating it by 90 degrees. So if you look at x plus iy, if you multiply this by I, you get -y plus ix. So we start off here. This is x plus iy. And so if I was going up this much now, so over here, this becomes my stuff over here. And then I move backwards this amount. So wait a minute. Did I do something wrong? Okay, so no, I'm going into negative real things like this. Okay, and then I'm going up like this. So it should be up like this. And if you check the angle, that'll be a 90-degree angle. So multiplying by I is really the same as a rotation by 90 degrees. And really what's going on here, e to the I theta, we have this rotation, starting off at 0, going all the way around back to where we started. All right, how is this going to help us? Well, let's look at the integration. And when we look at the integration, we have this is equal to 1 over 2 pi I. The integral, theta goes from 0 to 2 pi. I am a huge fan of overloading notation and putting subscripts in integrals so that you know what is changing. This is especially useful when you have lots of different things going on and it's not always clear what's fixed. z to the n is r to the n e to the I n theta. dz is going to be r e to the I theta I d theta. The I comes out and cancels with the I. I get an r to the n plus 1 that comes out. I have r to the n plus 1 divided by 2 pi. Integral theta goes from 0 to 2 pi e to the I n plus 1 of theta d theta. So you should be thinking about this as, cosine n plus 1 theta plus I sine n plus 1 of theta. When I integrate cosine and sine, this is an integer. So I have an integer number of periods. What am I going to get if I integrate over an integer number of periods? 0. Will I always get 0? There's one value of n where I will not get 0. What is that one value of n?
Negative 1.
-1. If I take n equals -1, I'm integrating the function 1. Normally, I'm not going to be kind enough to give you the following problem. Integrate 1 from a to b. Right? Fortunately, that turns out to be the most important integral in complex analysis. And the integral of 1 from a to b is b minus a. So the only value of n where this is not 0, because n is an integer, is when n equals -1. So when n equals -1, this integral is going to be 2 pi. The 2 pi cancels the 2 pi down here. Oh, wow, this is so nice. When n equals -1, r to the n plus 1, the r doesn't matter. And so this is going to just be 1 if n equals -1 and 0 otherwise. It should. You took complex analysis with me.
Well, but it also looks like
So nice to know I made a difference.
it also looks like the inner product that we studied when we were doing Fourier series.
Oh, it's very similar to that, yes. And there is a reason why, in terms of what we're going through the book, everything is having this Fourier analytic flavor. Everything is coming into these exponential functions. What we were doing before was, one or two exponential functions orthogonal to each other. And it all came down to when the exponent was 0 or not 0. So when we're integrating, what really matters is, do we have a 1 over z? If we have a 1 over z, then we have a contribution. If we don't have a 1 over z, we don't. What if I were to multiply this by 5? What would happen?
You would have 5.
Yeah.
1. And
Yeah.
it equals -1.
You just have the a propagate through. Right? Yes?
Is this kind of analogous to the weird things happening when you try to integrate 1 over x as compared with any other?
It is related in that there's not this nice antiderivative. So in a complex analysis class, what you'll eventually learn is if a function has a primitive, if it has an antiderivative, when you do an integral on a closed thing like a curve, you get 0. The function 1 over z does not have a primitive. It does not have an antiderivative. Why? The logarithm function cannot be defined on the entire complex plane. It can't be defined if you go all the way around, because e to the 2 pi I and e to the 0 both correspond to 1, but they would have different logarithms. So they like to use the word primitive for antiderivative in complex analysis. It goes nicely with the holomorphic for differentiable. Okay, so now that we have all of this, let's look at a more general example. Let's say f of z is the sum, n goes from n naught to infinity, of an z minus z naught to the n. So everything is fine except possibly at one point z naught. So if I want to take the integral 1 over 2 pi I about some closed curve about the point z naught of f of z dz, this is equal to 1 over 2 pi I integral over gamma of z naught. The sum, n goes from n naught to infinity, an z minus z naught to the n dz. What does this integral equal? And why is that true?
What's over there?
What are we doing?
We're switching.
We're switching, right. So if you had, oh, I don't know, like a whole semester, you could justify something like that. Right? So 1 over 2, so we'll do it this way. So it's the sum, n goes from n naught to infinity, a n 1 over 2 pi I integral gamma z naught, z minus z naught to the n dz. And now the only thing that survives here is the case when n equals -1. And so we were left with a minus 1. So we've reduced the integration to just figuring out what this one term is. That's good progress. But of course, we might have a function that has a pole at more than just one place. You know, we could have a function that has a pole at several places. And so all we have to do is we just have to extend this a little bit. How many of you remember Green's theorem? I cannot prove it, but if heaven exists and you're a mathematician and you do not know Green's theorem, I do not think you will gain admittance. So if you do not know Green's theorem, you need to remedy that, especially if you have to deal with 3 letters. And those 3 letters could either be these 3 letters or these 3 letters. You know, either one of those, you need to know Green's theorem. Okay? All right.
Oh, wait, I actually couldn't work that out.
Yes. You need to know Green's theorem. So imagine you have a function that has a couple of places where it blows up. And you want to take some curve like this. What matters is the places where the function blows up inside the curve. So the first thing we want to do is we want to say, if I have a nice function, if I integrate this about a circle or I integrate this about a strange shape, I get the same answer. And the reason is my function has an antiderivative except at this point. And so in this region between them, my function has a primitive. And when I evaluate what's going on in that outside region, everything is going to cancel. And what you get at the end of the day is that the integral on the outside is the same as the integral on the circle on the inside. Is you can basically deform the integration down. All that's happening is the action at one place. Now, if you look at this, of course, you're going, this is not a closed curve. So you go, fine. So to make it a closed curve, you draw a really small little thing there. You draw a really small thing there. And now what you do is you come in like this. And you reverse the direction of one of them. So maybe what I'll do is I'll keep going this way. I then come down on this one, come around here, come back out, and go around. And then I just have the slit get smaller and smaller and smaller, get closer and closer to each other. In the limit, those 2 pieces are going to align, and you're going to travel them in opposite directions. What happens if you integrate in opposite directions on the same curve?
This is what they were talking about in Ghostbusters.
Total protonic reversal. It's imagining all life is, it's swapping instantaneous in every molecule and every cell in your body exploding at the speed of light. Whoa, total protonic reversal. That would be an important safety tip, everybody. Thank you, Egon. Okay, so if you go in the opposite direction, the 2 integrals cancel. Okay? I know that movie by heart. You can give me any line in Ghostbusters and I will give you the next line. All right? So those 2 cancel, and then you're left with the integral over the whole thing is 0 because I have this curve now. And in this whole curve, there's a nice notion of an interior. And the function is holomorphic. The function is well defined there. It has an antiderivative. So the integral over the whole thing is 0. Well, that's the same as the integral over the outside minus the integral over the inside because I'm doing the integral on the inside the wrong way. So therefore, the integral on the inside is the same as the integral on the outside. So if you have a region where you don't have any if you don't have any poles, you can just pass from one to the other. So if I give you something like this, what you do is you make these little slits, and you come down and you do these little circular paths. Do I have to worry about the other one? Nope. Why not? Yeah, because it's not inside. And so, oops, I probably went this one the wrong way. And so what you can do is you can reduce the integration of a more complicated curve like this to just finding out the -1 term at these points. And all that matters is what's contained inside. And so the result you get is the integral of 1 over 2 pi I over some curve gamma of f of z dz is equal to the sum of the residue of f at the points zk. And so zk is the place where we have a pole. The residue, this is the -1 term in the Laurent expansion. So what I'm doing is I'm expanding my function at each point zk where it blows up. And at each point I look at what is the -1 coefficient, and I just add them. And this is an absolute miracle that it converts the integration to algebra. So theorems along these nature, they used to go by like the Cauchy residue theorem. It's really Green's theorem. And so what I'll do is I'll make available a lecture I gave in Calc 3 many years ago, Green's theorem in a day, where that's what's going on here. This is just Green's theorem.
Who's residue?
I'm sorry?
Who's residue?
That's from his dog. Okay, so this is almost everything I wanted to do. There was the one thing I wanted to do that I didn't get to today was dealing with logarithms. And so we've got about 2 minutes left, so I think there's enough time to just state why and just motivate what's going to happen tomorrow. All right? I've given it away, but why do I like to say the word logarithm? What do I like about logarithms? They convert products to sums. Anybody know any good product-sum relations in number theory? I'm sorry, the zeta function. Zeta of s is the sum of 1 over n to the s is the product over p, 1 minus p to the minus s inverse. It's screaming at you, take its logarithm. The log of zeta of s is going to be negative sum over p log of 1 minus p to the minus s. Now, I've told you enough times that whenever you see a product, your Pavlovian response is to do what? Take the logarithms. It turns out in complex analysis, whenever you see a function, your Pavlovian response is to take the logarithm, differentiate, and then integrate. It's called taking the logarithmic derivative. So take the logarithmic derivative in complex. Why is this worth doing? If I take the derivative of the log of f of s, we'll do f of z. We'll go back to normal notation. This is going to be 1 over f of z times f prime of z. Let's say f of z is an z minus z naught to the n plus dot dot dot. If I try to see what's going on, the denominator looks like an z minus z naught to the n plus dot dot dot. Over here, when I take the derivative, I'll get n z minus z naught to the n minus 1. The main term of this is going to look like n over z minus z naught when I do the expansions. So you'll pull a z minus z naught to the n outside. You'll then have a 1 plus z minus z naught plus dot 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 dot. Remember, the powers of n are increasing as we go to the right. When you integrate this, the only thing that matters is the lead term. When you integrate f prime over f, what you get is basically the order of the zero or the order of the pole. This becomes really nice. And what you do in number theory is you do integrals like this all the time, except rather than just integrating the function blandly by itself, you weight it by something convenient. All right, so this is complex analysis in a day. We have to stop because that's all we've allowed ourselves. We will then deal with applications of this to number theory on Wednesday. And we will see how this will essentially give us a proof of the prime number theorem. To make the proof really rigorous, we need some control over the location of the zeros, and we need some control over making all this complex analysis rigorous. It is not a surprise that the people who proved the prime number theorem were instrumental in proving results in complex analysis. Okay.